So let's continue our lecture on probability. So in this lecture, let's talk about conditional probability. So what do we mean by the term conditional probability? So the name itself says there is a condition involved. What is that condition? Let's take a simple example. Let's say you've gone to the hospital and you had a continuous let's say for example with the current condition, let's say you had a cough, a continuous cough, and you had breathing issues and you went to the hospital. Let's say you took the coronavirus test. So let's say for example you took the COVID-19 test. Now the question here is, let's say if the test comes out to be positive, then what is the probability that you actually having the the probability of actually having COVID? So remember that not all tests are good, which means that there is a chance that somebody, so you can be tested positive but even might not have the actual disease itself. So the same case, if you take another example, let's say let's take a simpler example. So let's say you have taken a mammogram and the mammogram comes out to be positive. Let's say A is the event where the mammogram is positive, B is the event where you have breast cancer. What are the chances of having breast cancer provided that your test came out positive? Remember that there are chances that even if your test came out positive, you might not have breast cancer. So this is the idea behind the topic of the concept of conditional probability. So here the condition is a prerequisite. So you already have something, and in that something, what is the probability of you having the extra part? So when we say here probability of B by A, what we mean here is that what is the probability of having, so what is the probability of having breast cancer if the mammogram was positive? So this here is an example of conditional probability. So here what happens here is that this can be written as probability B by A can be written as probability of A intersection B over the probability of A. So here this here is an example that we use, or a formula we use. So what happens when you want to calculate this? Let's say for example we have a problem here. Let's say that in this data that we used before, so what is the probability that a subject has no family history of mood disorders given that the selected subject is early? So let's take this data here. So let's take the example here. So here the question is, what is the probability that a subject has no family history of mood disorders given that the selected subject is early? Remember that it's already mentioned that the person is early, which means that we don't have to take the total. We only have to consider the population of the early age, right? So remember that given that, whenever you see the term given that, it means it's a condition. So that condition is that the person is already early, so he's an early age person. In that early age person, what is the probability that he has no family mood disorder? So this can be written as probability of A over E. The previous given condition can be written at the bottom, and the one that you are finding is written at the top. So how do we find it? How do you find the probability? So take the cases, the total cases of early cases. So the total number of cases in early, that is 141. Out of that, how many are early? So out of that early patients, how many are having no mood disorders? That's 28. So this is how you can calculate the actual conditional probability. So this is how you can calculate the conditional probability in any given problem. So the other formula that we can use is the probability of B over A can be written as probability of A intersection B over the probability of A. Here also you can use any of these problems. Most of the problems you can use this formula as well. or you can directly calculate the probability if you have the table in order, right? So this is, so B by A represents the conditional probability of B given A. So given, already A is given, so you are finding the, provided A is given, what is the probability of B. So another quantity that we define is the term relative risk. So relative risk is written by RR. It's the probability of B by A by the probability of B by A bar. So A bar represents the complementary event, is the complement of A, right? So this term is called relative risk. If the relative risk is equal to 1, then A and B are independent events. So A and B are independent events. So that's the idea behind the relative risk here. So I hope you understand the concept of the probability here. Next, let's talk about marginal probability. Marginal probability is when you have to break up probabilities. So if you have a single event, so some variable that you have broken up into m categories, you can categorize them into A1, A2 and A and so on until AM. So then the marginal probability of A is if you calculate each individual category, and then each individual category you have broken it into other n categories again. So then the probability of that event can be calculated as sigma of the probability of each individual event's value. So for example here, how do you calculate the probability of E? So E is split into 4 parts: A, B, C and D. So when you want to calculate the probability of E, can be written as probability of E intersection A plus the probability of E intersection B plus probability of E intersection C plus probability of E intersection D. Remember that we are splitting each event into its individual probabilities. So you can calculate it as 28 by 318 plus 19 by 318 plus 41 by 318 plus 53 by 318. So the final probability is 141 by 318. So this is one another way of calculating the probability of broken up events, right? So this is the idea here. So in the same way, now try to calculate the marginal probability of P of L. So notice that here you have to, so the formula is P of L is P of L intersection A plus probability of L intersection B plus probability of L intersection C plus the probability of L intersection D. So try this and make sure to solve the problem and see if you can answer the question. So next, let's discuss screening tests. So screening tests are the tests done to recognize whether you have the chance of getting a disease or not. So for example, when you take the mammograph test, so the mammogram test is the test for breast cancer. Right? So this is the idea behind test here. So in any test, the general concept, we define them as follows. So there are 4 variables that we define. So the first one is predictive value positive, or it's written as PV plus. The other is predictive value negative, it's written as PV minus. Sensitivity and specificity. So any test can be judged on its ability based on these 4 concepts. So let's say, for example, so let's take an example and try to understand this. So let's take the example of mammography itself and let's try to understand what all these variables mean. So let's consider T here as the test and D as the disease, right? So predictive value positive is the probability. So predictive value positive is the probability of, so it's the probability of having the disease when the test is positive. So remember that this is the probability of having the disease when the test is positive. So the condition here is that your test should be positive. Out of that, what is the probability of you having the disease? So that is PV plus. So PV plus is defined as the probability of a person having a disease given that the test is positive. So we call it predictive value positive. Predictive value negative is the probability of no disease when the test comes out negative. So we can write it as the probability of a person, so the probability that a person does not have the disease given that the test is negative is defined as the predictive value negative. So remember that here your test is negative, but what are the chances that when your test is negative that you do not actually have the disease? So that's the idea behind PV minus. The other two are sensitivity and specificity. So sensitivity is the probability of test coming out to be positive when you have the disease. So it's the probability of testing positive given that you have the disease. Specificity is the probability of test coming out negative when you do not have the disease. Probability of testing negative given that the person does not have the disease. So if you look at both definitions, there are tricky things that you have to understand. So in the first one, the given condition is that when your first thing is we are always testing the person. Already we have all tested the person, but we want to know whether he has the disease or not in the predictive value part. So we have already tested the person, either he comes out negative or positive, and we want to see whether he has the disease or does not have the disease. In sensitivity and specificity, we know the condition of the disease, but we want to check based on the test whether the test is reliable or not. So predictive values are generally used to represent the power of a test or the ability of a test to screen patients properly. The sensitivity and specificity are the ability of the test to check whether the test is valid or not. Right? So the validity of the test. So PV plus and PV minus depend on the reliability of the test, and sensitivity and specificity are used for the validity of the test. So these are the two things that you have to remember. Now this comes up the question, why would you have, so what would be the case where you would be testing positive but you do not have the disease? So we write two things, one is called false positive and the other is false negative. So false positive is when the test is positive but no disease. False negative is when the test is negative but has the disease. So for a patient who tests positive but does not exhibit any symptoms or does not have the disease, so we call it a false positive. For a person who tests negative but ends up having the disease, we call that a false negative. So these are the two differences that you will have to remember. Now, what is the idea behind the, so can we name them into formulas? So one way to give them formulas is by using the Bayes rule and relating both the quantities. So Bayes rule uses quantities to relate them, and we can write down the formulas for them. So how would you write down the formulas? For example, let's say T represents the test and T bar, so remember that T represents test positive and T bar represents test negative, and let's say D represents disease positive, D bar represents disease negative. Right, so based on this, what would be the PV plus value? So PV plus would be the probability of having the disease, so D by T, probability of D by T. PV minus would be the probability of D bar by T bar, so the probability of D bar by T bar. Sensitivity would be the probability of T by D. Specificity would be the probability of T bar by D bar. So these are the formulas that we use. So one way to represent PV plus, so we can use PV plus to represent it in terms of sensitivity and specificity. So we can mention predictive values in terms of sensitivity and specificity. So how would you write the formulas then? So PV plus can be written as sensitivity times X over sensitivity into X plus 1 minus specificity into 1 minus X. So we'll see what X means. PV minus becomes specificity into X over, so specificity into 1 minus X over specificity into 1 minus X plus 1 minus sensitivity times X. So these are the two formulas that we use for PV plus and PV minus. X here represents a term called prevalence. Prevalence is the probability, so the total number of people who actually have the disease. Who are diseased in a population. Right, so the X represents the prevalence. Prevalence represents the value, which is the total number of people that are in the population. So let's take a simple example and let's see if we can solve using that example. So let's take this example. So here they have given us the level of prostate specific antigen in blood is frequently used as a screening test for prostate cancer. So they have given us the following data regarding the relationship between positive PSA and prostate cancer. So now they are asking us to find sensitivity and specificity, PV plus and PV minus. Now remember the idea here. PSA test result represents test positive, the test here, and prostate cancer is the disease. So sensitivity, what is the formula for sensitivity? It's the probability of having the test positive when you actually have the disease. Right, so T by T. So probability of, so here what do we want here? We want to have all the people who are diseased, so only pluses, only count pluses. So the only plus values is 92 plus 46. So 92 plus 46. So that is a total of 138. Remember that we are only counting the positive disease, right? And positive test. Next, in that diseased people, in that total of 138, how many people actually have the T plus value? How many people actually have the test positive? So remember that here disease positive should also be there, test positive should also be there. So this is disease positive and test positive. So that value is 92. So sensitivity is 92 by 138. So sensitivity is 92 by 138. So I hope you understand. Let me do this again so that it's much more clear. So there are two things that we want. One is the total number of people who are diseased. So total number of people who are diseased is plus plus. So that is 92 and 46. So that 92 plus 46 is the bottom. Out of that, who are actually diseased, who have tested positive. So in the people who have actually diseased, how many have tested positive? So this tested positive is the first case. That is 92. So that value becomes 92 by 138. So that is the value for sensitivity. Next we want specificity. So specificity is the probability of testing negative when the disease is negative. So in the denominator we want all the people who are not diseased. So who are not diseased is minus and minus, that is 27 and 72. So the 27 plus 72. Out of those 27 and 72, how many people actually does not have the disease plus the test is negative? So these are the people who do not have the disease as well as minus and minus, that's basically. So that's 72. So that becomes 72 by 27 plus 72. So that gives you a value of 72 by 99. So that value is the specificity. Next we want PV plus. PV plus is the probability of having the disease positive over the test positive. Now in the bottom we want to know all the people who have tested positive. So now let me refresh this. Now let's look at only the people who have tested positive. So notice that this is positive and positive. So that is 92 and 27. So on the bottom part you get 92 plus 27. And in that how many people have tested positive who actually have the disease, meaning that who have the test positive actually have positive cancer. So that is 92. So you get 92 by 92 plus 27. So that gives you a value of 92 by 119. Next, PV minus. PV minus is the probability of disease negative given that the test is negative. Remember that we only want people who are negative tested now. So in this, who have negative test now. So only these two groups, the last two, that is 46 and 72. So that is 46 plus 72. Out of those tested negative who actually do not have the cancer, so that is negative. So that becomes 72. So that's 46 plus 72 is 118. So that's 72 by 118. So this is how you can calculate when you have frequencies. Remember that we are not talking about sensitivity and specificity formulas yet. So this is one way you can calculate from the formula. So that's the idea here. Next. So let's try another example. So now let's try this problem. So here, this is the problem that we are using the original formula. So these formulas. So we're going to use these formulas. Right. So let's try and understand this. First, notice the data here. So suppose 84% of hypertensives and 23% of normotensives are classified as hypertensive. Now remember, the disease is hypertension and the test is the automated blood pressure machine, so BP machine. Now notice that they are saying that 84% of hypertensives are classified as hypertensive, meaning that people who have the disease are tested positive. So remember that whenever you see the term hypertensive, that represents disease positive. Normotensive is disease negative. Now let's look at the case again. Let's look at the question again. So suppose 84% of hypertensives are classified as hypertensive. So which means that people who have the disease are being classified as hypertensive. So notice that here 84% here, what does this represent? 84%. So 84% represents the probability of having the disease. So having the disease provided the test comes out positive. Right, remember that they are already having hypertension and the machine has detected that they have hypertension. So this is sensitivity. So this value is the first value, which is 84%. Now the second value they have given is 23% of normotensives are classified as hypertensive. Remember that these are people who do not have the disease, they are being classified as the people who have the disease. So this is the probability of disease negative and test positive. So if you remember this sounds familiar. So if this sounds familiar, this is the topic of having no disease but the test comes out to be positive. So this is false positive. So but we know that specificity is the probability of test negative when the disease is negative. So if you take the normal rule of complement of a given value, so t plus by d minus becomes 1 minus the probability of t plus by d minus. So this is from the probability complementary set. The probability of a bar is 1 minus p of a. So this is the idea here. So that's the formula that I'm using. So that's the formula that I'm using here. So this becomes 1 minus 23% is, remember that 84% represents 0.84. 23% means 0.23. So that becomes a value 0.77. So you have the specificity, which is 0.77, and sensitivity, which is 0.84. The other value they have given you is that, notice that assuming 20% of the adult population is hypertensive. If you remember from the formula, I told you that a value called prevalence. Prevalence is the total number of people who are actually having the disease. So that value is 20%. So from the data that we have, it is given that sensitivity is 80%, specificity is 77%, I'm sorry, 84%, so specificity is 77% and X is given as 20%. So write down in the decimal forms 0.84, 0.77 and 0.20. Now what are they asking you here? They are asking you to find PV plus and PV minus of the machine. So PV plus and PV minus. So the PV plus formula is, so sensitivity into X by sensitivity into X plus 1 minus specificity into 1 minus X. So sensitivity into X is 0.84 into 0.20 over 0.84 into 0.20 plus 1 minus specificity is 1 minus 0.77 times 1 minus X is 1 minus 0.20. So that value is 0.84 times 0.20 over 0.84 times 0.20 plus 0.23 times 0.80. So if you calculate the value for PV plus, so that gives you the numerator is 0.168 and the denominator will be 0.352. So that would be about 0.48. So PV plus is 0.48, or you can write it as 48%. So this is PV plus. Next, how do you calculate PV minus? So PV minus is specificity into 1 minus X over specificity into 1 minus X plus 1 minus sensitivity into X. So specificity is 0.77 into X is 0.20 over 0.77 times, I'm sorry, this is 0.1 minus 0.20 times 1 minus 0.20 plus 0.84 times 1 minus 0.84 times 0.27. So if you calculate, you will get a final answer of 0.95. So the numerator is 0.616 by denominator is 0.648. So PV minus is 0.95. So this is one another method of calculating the data. So hope this cleared out the concept. So make sure to remember both these formulas. So if you remember both these formulas, this part will become easier. So this is the topic on PV plus, PV minus, sensitivity and specificity. So one another format you might get problems is, so you might have a disease on the top, test on the left, positive, negative, A, B, C and D. So this is only valid when you have this way. Now, so when you have it this way, sensitivity can be calculated as A by A plus C. Specificity can be calculated as B by B plus D. So this is the idea here. Specificity is D by B plus D. So this is the idea behind top. So in this table, C represents the false negative and B represents the false positive. So this is one way you can calculate from the formula. So this is another form that you generally end up with. So this is one other way to calculate from the table. So hopefully this clears out the doubt. So if you have any doubts again, so make sure to review the lecture again. So just turn it back a little and then watch it from the part that you're missing again, because this is a little confusing topic. So make sure to watch it back again. So let's take this example. So here a medical team wishes to evaluate a proposed screening test for Alzheimer's disease. So the test was given to random 450 patients with Alzheimer's and an independent random sample of 500 patients with symptoms of the disease. So the two samples were drawn from a population who were 65 years or older. So the results are below. So notice that the disease on the top, the test on the left. So now how do you find sensitivity? So notice A, B, C, D. This is the way you write it. So sensitivity is A by A plus C. So A is 436 by A plus C is 436 plus 14. So that is 436 by 450. Next, specificity is D by B plus D. D is 495 by 495 plus 5. That is 495 by 500. So calculate it as a percentage. So 436 by 450 is 0.9688. 495 over 500 is 0.99. So this can be written as 96.88% and this is 99%. So this is how you can draw the sensitivity and specificity values from the problem. Now you can also draw PV plus and PV minus, provided if in the problem prevalence is not mentioned. So let's take this data. So let's go back to the formula part. So in this problem, how would you find the value for X? So X is written as P of D. So the probability of disease. The total number of people who have the disease is 450 out of 950. So the value is 450 by 950. So this is the value of X. So when you calculate 450 divided by 950, that gives you 0.4737. So this you can use. Now let's take the values that we have. So we have a sensitivity of 96.88% or 0.9688, specificity of 0.99, X value of 0.4737. So again PV plus becomes, so sensitivity into X by sensitivity into X plus 1 minus specificity into 1 minus X. PV minus becomes specificity into 1 minus X over specificity into 1 minus X plus 1 minus sensitivity into X. So sensitivity into X is 0.9688 into 0.4737 over 0.9688 into 0.4737 plus 1 minus specificity is 0.01 times 1 minus X is 1 minus 4737, and here again specificity is 0.99 into 1 minus 0.4737 over 0.99 into 1 minus 0.4737 plus 1 minus specificity is 1 minus 0.9688 times X is 0.4737. So when you calculate the full value, so when the calculation is done, you should get, so PV plus would be 0.93 and PV minus would be 0.996. So try calculating on your own and try to see if you can get your answer. Remember, X represents the probability of having the disease. If you have the disease, which means the total number of people who are diseased, 450, divided by the total number of people in the entire sample, that is 950. So 450 by 950. That can be used as X. Right? So this is when you have a table, this is how you can calculate sensitivity, specificity and PV plus and PV minus. So hopefully that was clear. So with that we end this lecture on probability.